Okay, so this is lecture 14 or 15? 15 or 14, I don't remember, so I just put some number here. Anyway, so I think till now we have looked at two variable functions, right? Functions of two variables, x comma y, and we looked at limit of a two variable function, continuity of a two variable function, right? And so you saw that you can plot it them as a surface and so on. So z is equal to f of x comma y. Now we also looked at differentiability in terms of, so differentiability we defined with respect to x, with respect to y. So actually we got partial derivatives, right? And then second order, higher order partial derivatives and so on. We described those things. But still I have not given you the flavor of, so I gave you the idea of tangent at a point. So normally, which is a plane on a surface, right? Two variable function, you can plot it as a surface, and corresponding to tangent there, here that it will be a tangent plane. There it's a tangent line, right? Those kind of differences you observe. Now, before giving you, so in case of single variable calculus, you saw that rate of change. How do you describe rate of change, right? You can describe in terms of differentiability, but here there are now partial differentiation with respect to x and with respect to y. So how do we define that, right? So we define what is known as directional derivative, okay? And then I'll give you that idea. So that gives you an origin of something known as vector calculus, okay? So I'll give you about that idea. But before that, so in order to build those concepts, I need to first complete some more differentiation things. So as you remember, last time we have shown that a two variable function z is equal to f of x comma y is differentiable at a point, say a comma b, if partial derivative exists, right, and are continuous. Remember that definition. This was something a stronger condition, right? First of all, partial derivative should exist and should be continuous, right? I think I gave you without any proof, but that's all. So, so first, now today I am going to define total differential. What is total differential? And then there are, so total differential means now we are looking at rate of change of z actually, right? d of z, okay, where z is a function of x comma y, right? How do you find total differential? And then there are a couple of chain rules, because there are now so many derivatives involved. What function is, so some function, so a function may be having two variables, and each variable may have some other functions involved. So how do you do the differentiation? So basically there are three important chain rules which are important. So I'm going to describe that after describing total differential. And then we look at the homogeneous functions. There is a special kind of two variable functions which are homogeneous. Okay, and I think I'll show you pictures of one or two also, like dog saddle and monkey saddle. Okay, so where a monkey will sit and a dog will sit, what is the curve? Okay, that can describe. And then we talk about Euler's theorem for homogeneous functions, and then we do directional derivatives. So we have enough thing, right, to do. Let us start. Okay. So we start with z as a function of x comma y. So we know that x and y are independent variables, right? So we can talk about d of x and d of y, right? So total differential dz is nothing but f of x dx plus f of y dy. In other words, del z over del x dx plus del z over del y dy. Okay, so this is nothing but total differential, right? Forget about that line that has come, but z is a function of x comma y, right? So total differential dz is del z over del x. You see, if this variable is not there, this is nothing but del z only, right? Because it's the same thing, but then the del x will become dx, right? So dx ds will cancel out, you will get dz, you will get dz. That kind of thing is there, algebraic manipulation. So essentially, because there are two variables involved, the definition has been extended, right, like this. Total differential d of z is nothing but partial differentiate with respect to x times dx plus partial differentiate with respect to y dy. Similarly, in fact, if it is a three variable function, so suppose w is f of x, y, z, so we can write down dw is equal to delta w over delta x dx plus delta w over delta y dy plus delta w over delta z dz. Right. This is a two variable case. Two variable case, and this is three variable case. Okay, so this is how, I mean, you can generalize it in a bit higher one also. Now I'm going to describe certain chain rules which are important, because actually, you know, you will see that some of these chain rules are very important when we do multiple integrals with, you know, n-fold integral or, you know, three-fold integral and so on. So chain rule. So we know that dy by dt is equal to dy by dx and dx by dt, right? Right? You know this fact. From single variable you might have used quite a lot. And I am not proving any of these things. Similarly, for two variable also I am not proving any of these things, but because if you do that, it will take a couple of months, right? If the whole calculus will expand anyway. So this is there, right? So basically you can think of loosely that dx will cancel out, you will get dy by dt, right? Those kind of things, right? By the way, who gave this idea that you can take the differentiation as independent variables, right? This is a very marvelous idea, you know, that you can treat like this. Anyway, so what will happen in case of two variable? Okay, this is a single variable formula. So I am going to describe first rule 1. Our function z is a function of two variables x comma y. Suppose x is a function of t and y is a function of t, some function. So how do we differentiate, right? So in that case, the chain rule says that dz over dt is equal to del f over del x dx over dt plus del f over del y dy over dt. Now you observe that here this is partial differentiation. Can you tell me why? Because there are two variables, right? Two kind of derivatives are there. Here actually there is only one, dx over dt, right? So it has to be one because x is only function of t. So when you differentiate, it comes d over dx, right? D over dt. Similarly here also dy over dt, right? So this is a first chain rule. When we are differentiating dz over, so z is a function of x comma y and x and y are two separate functions of t. This is how you can differentiate. So in case of a single variable, suppose y component is not there, so this portion will not be there, it will reduce to the single variable case, right? Straightforward, right? So you can see the analogy, right? Because now there are two variables involved. First you differentiate with respect to x and then dx over dt plus y and dy over dt, right? So fairly easy to observe, no problem. Now we go to the second chain rule. Now this time I assume that z is a function of x comma y as usual. So this is rule 2. And now x is function of two variables. And y is some other function of two variables. Okay. So now, since z is a function of x comma y, initially x was function of t and y is function of t. So we know how to differentiate, right? But now, since x is a function of two variables and y is function of two variables, z will also, when we differentiate, we have to differentiate with two variables, right? With respect to s and with respect to t. I need to find the formula, right? So, the first thing will become del z over del s. And this will be what? Del z, del z over del s is equal to del z over del x over del s plus del z over del y over del s. Similarly, we will have del z over del t is equal to del z over del x over del t plus del z over del y and del y over del t. Right. So this is quite obvious, right? This is quite obvious because there are two. Each one is a function of two variables. So when we want to differentiate z, I have to differentiate with respect to s and with respect to t. So I should have a formula. Now everywhere there is a partial derivative, right? Because there is no single variable thing here, right? So everything has to del z over del s. Similarly, and it is quite obvious. You see, this simple chain rule for single variables kind of thing you are generalizing, right? So that's rule number 2. As an exercise, if z is equal to e raised power x times sine y, example, x is equal to say s times t square and y is equal to s square times t, find del z over del s and del z over del t. I leave is an easy exercise, you can find out, right? Just compute the derivatives. Remember, partial derivatives works like that. If you differentiate with respect to one variable, other variable has to be constant. Treat other variable as a constant and do differentiate, right? Okay, so very simple thing. And obviously this is so simple that I am never going to ask you in the exam, right? This is a very simple calculation, right? So that's why it's okay, right? Your exam should have some beauty. Okay, so this is straightforward, right? Okay, let me describe now chain rule 3. Rule 3 is actually a general rule. Rule 3, general chain rule. So suppose u is a function of n variables. You see, x1, x2, xn, and xj is differentiable function of m variables. अरे यार, या तो ये ऊपर जाएगा या वो ऊपर जाएगा, राइट? right? So normally we write it like this. I am not writing the whole language, but it says that u is a function of n variables. So we are generalizing z is a function of two variables, right? F of x comma y. Here we are calling that function u when we are doing with n variables, okay? Because if you take z, you know, we are more, right? So u is a function of n variables x1, x2, xn, and each xi, right? Each xj is function of m variables, right? The generalization of rule 2 kind. So now when we differentiate u, so we have to differentiate u with respect to t1, t2, t3, tm, right? And we can have a general formula, right? I'm just writing the general formula. Del u over del ti is equal to del u over del x1 over del ti plus del u over del x2 over del ti plus dot plus del u over del xn over del ti. And obviously 1 is less than equal to I is less than equal to m, right? So this is the most general case that is possible, right? Because you have to differentiate for each of m variables, right? Because now you will become function of all those things, right? So easy to calculate, very obvious. You don't have to even memorize. When you are dealing with the functions, you can directly start using it, right? As long as you know what you are doing it, right? Again, you can do a couple of examples, but these are very trivial examples, so you can always do it. Okay. Now I think in the single variable calculus, when you do some sort of substitution, right, in the function, right, and do differentiation or something like that, right? So you have to, basically when you're doing the change of variables, right, the similar formula exists here also for two variable case, and here it is a little bit lengthy, not complicated. I will say that it takes a lot of writing. So people have described a shorthand. See, mathematicians love shorthand, and they described a shorthand for such kind of large expressions, and they call it Jacobian. Jacobian is the name of a mathematician. It is after his name. So I'll show you those Jacobian things, and they are pretty useful when you do multivariable differentiation or integration. Okay, n-fold integration, you change the variable, do substitution, and then this Jacobian part come out of it, right? So let me describe what is Jacobian. So again, the whole thing can be done for n variables. I am just taking simple case, 2 variable. Okay. Change of variables. So we have a 2 variable function f of x comma y. X is a function of s comma t, and y is a function of s comma t, right? So by chain rule, we know that del f over del s is equal to del f over del x over del s plus del f over del y over del s, right? I call it equation 1. This is the first chain rule, right? We are differentiating f with respect to s. Okay. Similarly, we can differentiate f with respect to t. This will become del f over del x. Yeah. Del f over del t is equal to del f over del x over del t plus del f over del y over del t. These are the 2 equations. Okay. So we have del f over del s and del f over del t. If I ask you find del f over del x and del f over del y in terms of del f over del s and del f over del t, can you do that? So I am saying that find an expression from these two equations. Okay. So I think using simple algebra, right, you can calculate this, you can solve the equations, right? You know how to solve the equations, right? So what we want, remember, I want value of del f over del x and del f over del y in terms of del f over del s and del f over del t. So I want the value of this. I want del f over del x, this is a question mark, and del f over del y, this is a question mark. I want to find these values from these expressions, and these values will be in terms of del f over del s and del f over del t. Del f over del s and del f over del t, right? So that means del f over del s and del f over del t is known to you, right? And what you want to find, it's unknown. You can solve the equation, right? So essentially I'm going to use one formula. I think you have read it in your JEE examination preparation, but let me show you. Del f over del t, del x over del s minus del f over del s, del x over del t is equal to 1 over del x over del s, del y over del t minus del x over del t, del y over del s. Have you seen this formula? Cramer's rule, कुछ सुना था ना? Remember? We have used that. Questions are there, so you can find. Now from here, I can find. You see, because everything is in terms of s and t here, so del f over del x is this divided by that quantity, right? Similarly, we have the other one, right? It's easy to find, right? अगर नहीं मालूम है तो it's easy exercise. चाय भी तो पीनी है शाम की, right? You can do that. Cramer's rule business, right? So, if forget about this line, you know, I am very bad in writing. This comes automatically, you know, and I don't know, right? So, okay. So this is a nice formula. Now, actually, you see that this kind of expression is coming everywhere in the denominator. So maybe we can do some sort of shorthand. And this whole expression is known as Jacobian. There is a Jacobian symbol, you know, which I will describe. So it's easy to write down. So let me show you what is that symbol. Okay, so basically you see, if you look at any of the denominators, say for example this can be written as nothing but determinant of some 4 variables, right? Determinant, you can arrange these 4 variables in a determinant, right? So you can compute the determinant kind of thing, right? So everything can be written in terms of determinant. So it's easy to think. So if we write something like this, if J is equal to del x over del s, del x over del t, del y over del s, del y over del t, this whole determinant, right? I can write it like this: del of x comma y, del of s comma t. In notation, this is known as Jacobian of the variables, right? This kind of notation I can use. all those expressions, because you see this is nothing but del x over del s into del y over del t minus del y over del s into del x over del t, right? That whole denominator thing that is coming up, right? So we can use this shorthand notation. This is known as Jacobian. So now if you use this kind of notation, the whole thing can be summarized as this. Del f over del x is nothing but 1 over j. J is this quantity here, you see. I mean this quantity here. One over j del of f comma del, so fy s comma t. So basically x, y, s, t variables I am denoting with capital J. So this is coming here, and del f over del y is nothing but minus 1 over j del of f comma x del of s comma t. Okay. So these are the shorthand. Okay, from the here. So actually, for this del x comma y and divided by del st. So this notation I am using capital J. But similarly, notations are there for other variables which I have, which are here and here. So what does this mean? Del f over, from there you see, del f over del s, del f over del t, then del y over del s, del y over del t, right? You can arrange in the determined fashion, right? Just shorthand I am using, nothing more than that. It's a very simple thing. Okay? Okay, so this whatever we have done, change of variables for two variable functions, right? So it will be nice if you can do it for 3 variable. Suppose f of x comma y comma z is there, and x is a function of capital F u v w, y is a function of u v w, and z is a function of u v w. Find similar formula. Only thing is now Jacobian symbol will be having 3 variables, right? So you have to expand. Determinant will become a bit larger, calculation will become a little bit messy, but that's okay, right? 1-2 घंटा लगेगा आराम से. मुश्किल नहीं है, थोड़ा सा लिखना पड़ेगा. It's just lengthy, okay? Calculations, right? You can have a similar formula for 3 variables. I think in most of your daily calculations, 2 variables and 3 variables is enough. I'm not going to go for any higher n variable things in that, because it's first year course, right? So 2 variable is okay for me. I'm not going to even worry about 3 variables. But since case 2 is there, so case 3 maybe you can look at it, right? Curiosity hoti hai na, right? What will be the formula for 3 variables? Probably ChatGPT will give you the answer, right? Anyway. Okay. Then there is another interesting thing. We call what is known as implicit function. I don't know whether you know about it. So when function is something like this, okay? Okay? So now basically in general a function is given like this. So maybe x square plus y square is equal to 0. That is a 2 variable thing. So that is a kind of denoting some sort of curve or something, right? In this case this is a circle, right? So x square plus y square is equal to a square. So circle of radius a, right? Those kind of curves are there. Then in this case, differentiation chain rule is, if you want to differentiate this, del f over del x dx over dx, right? del f over del x dx over dx plus del f over del y dy over dx is equal to 0. We can differentiate this function. This is a chain rule 1. So dy by dx is nothing but minus del f over del x divided by del f over del y, or we call it as minus of fx, differentiation of x with respect to differentiation of f with respect to x and of y with respect to differentiation of f with respect to x divided by differentiation of f with respect to y, where obviously f of y is not equal to 0, otherwise it will not make sense, right? Okay, so same thing can be done for 3 variables also, but by the way, I just want to give you one example. X cube plus y cube is equal to 6xy. So we can say that f of x comma y is x cube plus y cube minus 6xy equal to 0. So dy by dx you can find easily minus f of x divided by f of y, which is minus x square minus 2y divided by y square minus 2x. Right? These are very simple. High school, I mean not even high school, class 8th, right? You know the formula, you just use it, right? Simple thing, right? कोई एप्सिलॉन डेटा का फ्लेवर नहीं है तो मेरे को मजा नहीं आ रहा, right? So the simple calculation, right? Obviously I'm not going to ask such simple thing ever, right? So okay, so I think now we are ready to describe what is known as homogeneous function. So two variable functions which has certain degree properties, they are homogeneous function. Let me give you the definition, then couple of examples. Homogeneous functions. A two variable function f of x comma y is called homogeneous of degree n. Of degree n if it can be written in any of the following forms, that you replace x by lambda x and y by lambda y, and you will see that lambda raised for n has come out. Okay, or either this or f of x comma y can be written as x raised for n times g of y by x, or that f of x comma y can be written as y raised for n of g of x over y. A homogeneous function. So what a function is given, you replace x by lambda x, y by lambda y. See what power of lambda comes out. So let us take an example. Suppose f of xy is x square plus xy plus y square. Is it a homogeneous? You can see that here the degree is 2, here the degree is 2, and 1 degree of x, 1 degree of 1, right? So it looks like homogeneous. Now you just substitute, okay? F of lambda x comma lambda y will be what? Lambda square times x square plus xy plus y square. Lambda square times f of x comma y. Right? So this is f is a homogeneous function of degree 2. Right? So beautiful t-type problem. Could we give an example of a function which is not homogeneous? बना सकते हो? Which is not homogeneous. By the way, I will give you one more example. Okay, दे ही देता हूँ actually. तुम भी क्या याद करोगे? Is this a function homogeneous? Now if you replace x by lambda x, y by lambda y, there will be an issue, right? You cannot separate power of lambda, right? This is not a homogeneous function. So why we should study these functions? They have some special properties which are listed or given by Euler's. They are called as they are known as Euler's theorem. It says that if f of x comma y is a homogeneous function of degree n, and suppose f has continuous partial derivatives of order 1 and 2. So first order del f over del x, del f over del y, or second order del square f over del x square, and so on. First order and second order partial derivatives are continuous. Then we have this property that